So welcome to Math 355. This is section 1, lecture 6. And so what we're going to do is we're going to start the experiment today of having one class devoted to lecture, one class devoted to just doing lots of worked out problems. You're welcome to come to both. I will make both videos available. Since this is essentially giving us 2 extra classes, there will be no classes next week to give you time for the extra 2 classes that we're doing today. So next week we'll have no physical classes. It'll just be a chance to, catch your breath, see how this is going, and see if this is a good, effective way to use our class time. Because the advantage of this is that eventually we should be able to do more proofs and more examples by moving more of the standard material to doing at home, or than just watching the video where I'll go through the standard material in one class, but not in both classes. Okay, so this will be a more standard lecture today. And then on Thursday, this section will have the more, let's just do lots of problems. As I said, you are welcome to come to both. All right, just going to make sure that it actually is recording. It looks like it is recording. Excellent. Okay. So what we're going to do today is we're going to start the next major topic of the course. We're going to start looking at rings. And so the idea is to generalize things we know. And if you think about it, what do we know best? We know numbers. Which numbers? The integers. And so we start off with the integers. Everybody know why we denote the integers with Z? It is German for Zahl, for number. Anybody know why we use Q for rationals? Quotients. Anybody know why we use N for natural numbers? That one's not so bad, right? And so the integers are going to just be numbers of the form, -2, -1, 0, 1, 2, ... The quotients are going to be numbers of the form P over Q. P and Q are integers, and Q is not 0. And then, of course, the natural numbers, it's either 0 or 1, ... from that point on. As to, do you want to consider 0? So what's nice is the integers have 2 different properties. They have addition, with a plus, and they have multiplication, which we denote either with a dot, a cross, an asterisk, lots of different ways of denoting it, or nothing. If you have a program in something like Mathematica, if you write 2 numbers next to each other with a space, it's implicit that you're supposed to multiply them. And so it turns out it's very nice when you have multiple operations. And you can ask, how do these different operations interact with each other? And so can you look at other objects where you have multiple operations? So can anybody think of something from linear algebra where you might have multiple operations between your objects? Yeah, with matrices, right? Matrices, you have matrix multiplication, or if you want to just be a little bit informal, multiplication. And you also have just the standard matrix addition. And so we again have a set that has 2 different operations. And then, of course, when you have matrix multiplication, matrix addition, what you could do is you could ask, well, what if I wanted to multiply matrices by real numbers or complex numbers or rationals or integers? Can I do that? And we define it by component-wise multiplication. If I want to multiply a matrix by 5, I multiply each entry by 5. Can I take in general a matrix and just add the number 5 to the matrix? They have different dimensions. A matrix is typically going to be, n by m. And so I can only add another object that has the same size. But we do define, scalar multiplication to just multiply every component by that number. Think of it as, I have a vector. If I multiply every component of the vector by 5, it's the same as stretching its length by a factor of 5. And so we have a bunch of definitions of a ring. So you should have looked at this before class today. This doesn't mean that you should be able to recite these from memories, but you should have, for today's class, read this and at least been aware of what is a ring and what are the properties. So a ring is a set with 2 operations, which we'll generally call addition and multiplication. And we write addition typically with a plus sign. We write multiplication either with a dot or with just nothing at all. And when there's nothing, that's just implicit for it, just multiply them. And we want it to satisfy the following operations, or the following axioms, sorry. So the first is the set R, where the addition law plus is an abelian group. So what does it mean to be a group? What four properties do I have? Closure, what else? Identity, inverse, and associativity. And now, a lot of times it's clear what's going on, but it's not bad to be extremely specific with your notation in the beginning. We're going to put a 0 for the 0 element, and we're going to put a subscript R on it to say that it's 0 with respect to the ring R. If we have multiple rings in play, it might be valuable to know this is the 0 element with respect to the ring R versus the ring S or the ring R prime. We've seen this already with identity elements when we've had the group G and G prime. We sometimes use E and E prime, or we might use E1 and E2 to represent the identity elements of the different groups. So we sometimes put in this subscript to just remind ourselves where it lives. So this is the identity. So what does it mean for 0R to be the identity under addition? What does that mean? Sure, so if 0 sub R is the identity for R under addition, what does that mean? Good, so for all R in R, R plus 0 sub R equals 0 sub big R plus R equals little r. That's what it means to be the identity element. What do you think might be true about it with respect to multiplication? Yeah, zero times anything is 0. So maybe the additive identity, maybe that functions as a 0 element under multiplication. And that's something we'll return to in a moment. The notation is definitely meant to be getting you to think along those lines. The next is that the set R is a multiplication with its multiplication law is almost a group. So it almost satisfies the four properties. It has closure. It has identity. It has associativity, not necessarily inverses. Can somebody give me an example of a set that's almost a group where you don't necessarily have inverses? The natural numbers. And so the natural numbers under multiplication would work. At least if we don't include 0 as a natural number. So we could do, for example, the non-zero rationals. If you take two non-zero rationals and multiply them, it's a non-zero rational. And is that almost a group? Does it satisfy all the properties but not necessarily inverses? So would the non-zero rationals satisfy all of the properties, closure, identity, associativity, and not necessarily inverses under multiplication? What do you think? Are the non-zero rationals, are they closed under multiplication? Do they have an identity? Are they associative? Do they satisfy these three properties and not necessarily inverses? Yes. Do they satisfy inverses? The non-zero rationals. Is the inverse of a non-zero rational a non-zero rational? Yes, right? Just because it doesn't have to satisfy inverses doesn't mean that it can't satisfy inverses, right? The group of, it is a group. It's the group of non-zero rationals. Now, I could also do as an example, the non-zero integers. And that would be a better example where I don't have inverses. The inverse of 5 under multiplication is 1/5. and that's not a non-zero integer. So just because it doesn't have to have inverses doesn't mean it can't have inverses. Okay, the next is that there's an identity element 1 sub r satisfying 1 sub r times a equals a times 1 sub r equals a for all a. So there's a multiplicative identity. And then we have the associative law under multiplication. A times b times c is ab times c. Okay. We're not explicitly stating closure here, but because the way the book defines multiplication, it takes elements of the set and returns an element of the set. In the definition of multiplication, it forces it to be closed. So that's why they're not isolating closure explicitly here. It is closed. The next is we have the distributive law. For all a, b, and c in R, a times b plus c is a times b plus a times c. And similarly in the other direction. So this is the first new law that mixes both the addition and the multiplication. And then there's another thing which might be true. It might be commutative. It might be that a times b equals b times a. If that's the case, then we say the ring is commutative. What about a plus b? Will that always equal b plus a in a ring? Yes, because by definition, a ring is an abelian group under addition. So by definition, I'm only considering objects to be a ring if they are a abelian group under addition. It is almost a group under multiplication. Now, we know that there's got to be some issues with multiplication. Which element might have trouble having an inverse? So which element do you think is going to be hard to have an inverse?
Element in what?
In R, under multiplication, which element do you think we're not going to be able to find an inverse to? 0, right? Anything times 0 should be 0. So, if we believe anything times 0 is 0, there's nothing we can multiply 0 by and get an inverse. So we don't expect a ring to be a multiplicative group under, just looking at the elements under multiplication. But maybe if we look at the non-zero elements, that might be a multiplicative group. So that could be our hope. Okay. And so we'll do a lot of examples later. Let's just start off with a really nice photo. Oh, okay, so it changes size. It's just a little bit. Okay. So here's proposition 3.2. They only prove part A. We'll do part A and follow the book, and then we'll do part B. So imagine R is a ring. So it has all those properties we saw just a moment ago. And then it's essentially saying the two properties you would expect to hold. This is good notation. If you take the element 0 sub r, and 0 sub r is the identity under which operation? So 0r is the identity under addition. We are thinking of it as a 0 element. And so the hope is that if we multiply anything by the additive identity, we should just get back the additive identity. Or in other words, this is really looking like 0 should be. So that's what A is saying. 0 times A is 0 for any A in the ring. And the next is negative A times negative B equals A times B. In particular, if you take negative the multiplicative identity and multiply that by A, you get negative A. So it's important to just unwind, what is this actually saying? What does negative A mean? So negative A is the notation for the additive inverse of A. So it means negative A plus A equals A plus negative A equals what? 0. So that's what the notation means. When we do multiplicative inverses, what would the multiplicative inverse of A, how would we write that? A to the minus 1. So again, it's just important to think of the notation we use. Notation should be good, right? Negative A times negative B should just be A times B. You know, we would hope for something like that. That's what property B is saying. How can you go? Okay. So let's prove A first. So let's just go through the proof very slowly. So we want to prove that when you multiply anything by 0, you get 0. Okay. So the first thing they say is, let's let A equal A times the multiplicative identity. So that's the first step. Well, that's true just by the definition of the multiplicative identity. This might remind you of some proofs from your geometry class, the old statement reason proofs. You know, for everything here, you give some reason over here. Did anybody do statement reason proofs in geometry?
I did, but I was like 13.
Right. It's been a while. This is why I want to spend time and explicitly write what's in the book. This is a really nice way when you're starting to make sure everything you do is justified. Every time you have a statement, on the right-hand side, you give the reason, why is it true? Why does A equal A times the identity element? Because the identity element is the identity for multiplication. This is the definition. And then we can say the identity element is the same as the identity element plus the additive identity 0. And that's just because that's the definition of what it means to be the additive identity 0. I can add 0 to anything and I don't change its value. The next thing is we now use the distributive law. A times a sum is the sum of the products. So then we get A times the identity element 1R plus A times the identity element 0R. They're different identities. Yes or no?
0 and 1.
1 and 0 different.
They do the same thing, but under different.
They're defined in very different ways. 1 sub R is defined as the identity under multiplication. 0 sub R is defined as the identity under addition. Have we shown that they're different? No. They have different notation. We think that they're different. In almost all settings, they would be different. You could ask, what would it mean if they were the same? So as an example, let's let R just be 0. Under addition and multiplication. Is this a ring? Is R an abelian group under addition? Closed. Associative. It has an additive identity, which is 0. And everything has an additive inverse. Because the only element is 0. 0 plus 0 is just 0. So what is the identity element? It's just 0. What about multiplication? Is it closed? Yes. Is it associative? Yeah. Is there an identity? Yes. 0 times R equals R for all R in R, right? It's really strange, but there is an identity. What about inverses? You could even say that it actually has inverses here. We don't need to show that. Distributive law is easy to show. This is an example of a ring. And so, oops. So this is a ring where the identity element is equal to the identity element. And by that, I mean the additive identity element is equal to the multiplicative identity element. This is going to be an extremely boring ring. That's a technical term, right? If the additive identity is the multiplicative identity, this is not going to be that interesting. But it is a case you have to be prepared for. And again, this is one of the things I really want to highlight in this course, how easy it is to make an assumption. That when we're looking at this, did you just assume when you were looking at this that the additive and multiplicative identities are different? They've got different names, they've got different notation. But technically, we never proved that they were different. And it is possible that they could be the same. So when we're going through these arguments, you have to be very careful not to accidentally put in additional assumptions. Okay, so we know that we had the third step, we used the distributive law. And now to get the fourth step, A times the multiplicative identity is just A. And then A times 0R, we don't know how to simplify that yet. 0R is defined as the identity under addition. We have no knowledge yet of what A times 0R is. In fact, that's what we're trying to prove. So now what we want to do is we want to subtract A from both sides. And the reason the author puts subtract in quotes is really we define everything through addition. Subtraction is really the same as adding the additive inverse. So when we say subtract, what it really means is take the additive inverse, and we're using the notation negative A. When you see negative A plus A, you want to pull out -1 from A, you want to pull out a 1 from A and add them and say that's -1 plus 1, which is 0. And that's essentially what we're trying to do here. So we're trying to mimic what you would do with the standard numbers. So we add negative A to both sides. Well, when we add negative A to A, that's going to give us the additive 0 element. And then on the right-hand side, okay, so 0 is negative A plus A. And then from over here, the A plus A times 0R, we've added negative A to that as well. So really, this over here is coming from A plus, I guess we're doing it on the left. Negative A plus A is coming from that. And then this part over here is coming into this line as negative A plus A times 0R. That's where these two lines are coming from. Okay, so 0 is equal to what happens when we add negative A to this, negative A plus this. And now what we do is we use the associativity of addition. And now we have lots of parentheses. We have the sum of negative A plus A times 0R. And negative A plus A, that is 0 sub R, because this is now just adding a number and its additive inverse, so we get the additive identity. And so now we get 0R plus A times 0R. But we know 0R is the additive identity, so when we add that to anything, we just get back whatever we're adding. So when we add 0 sub R to A times 0 sub R, we just get A times 0 sub R. And so we see 0 sub R, the multiplicative, the additive identity, is equal to A times 0 sub R. So whenever you multiply anything by the additive identity, you get the additive identity. So essentially, if you multiply anything by 0, you get 0. Okay? This is a lot of work to prove what you would just expect to naturally be true. And we're really using, the properties. We're using the distributive law. We're using the associative law. We're being very careful to keep track which are the identities for multiplication, which are the identities for addition. Okay. Any questions about this proof? So there's a lot going on in this proof. It's a lot more than it looks. All right, so now, because we're going to be flipping, we actually have a little bit more time because I'll have you watch the video for the theory for next class. So we can actually talk about the proof of part B. Negative A times negative B equals A times B for all A and B. In particular, we have negative 1 times A is negative A. So can you think of a good way to get the in particular part from the first part? So the claim is negative A times negative B equals AB implies negative 1R times A equals negative A. You see how to get that. And to make things a little bit easier, rather than using A, let me use a different letter over here. Let me use the letter X. So if we want to show you the in particular, that's giving you a hint. It's basically saying this next part should follow from the first part. So if we choose A and B appropriately, we should be able to get this. What should we take A to equal? We take equal. What would you try for A? One. Because if you look what we have on the right-hand side, we want negative 1. And so if we take A to be 1, that gives us the negative 1. What should we take B to be? We want to multiply this by X. So what should we take B to equal? Negative X. Because what is the additive inverse of the additive inverse of X? The additive inverse of the additive inverse of X is X. Right? I'm not saying negative 1 times negative 1 is 1. I'm saying negative X means the additive inverse of X. And then I want to take the additive inverse of negative X. Well, that's X because X plus negative X is 0. So this is similar to, what is the tangent of the arctangent of X? X, right? What's the exponential of the natural log of X? It's just X. These are inverse functions. So if I take the additive inverse of the additive inverse of X, I just get back to X. So now when I plug this in, this yields negative 1. And then we're taking B to be negative X times X is just going to be A times B. So it's just going to be 1R times negative X. But when you multiply anything by 1, you just get back itself. And so this is how the in particular follows from the first part. If we can show negative A times negative B equals A times B, then we immediately get negative 1 times A is the same as negative A. So this is a really good example of trying to figure out how do I read things to figure out what are good choices of items. I'm given that we want to show negative 1 times A is the same as negative A. So this gives me some idea of what do I want A and B to equal. It can be a little bit confusing because when you're using this, you would actually be taking A to be the identity element 1, and you'd be taking B to be negative A. That's why I switched, and rather than using A again on the right, that's why I switched to X, to just make it, I think, a little bit easier to follow. Any questions about this? So this is how we handle the in particular. My son is taking linear algebra right now, and they have a lot of problems where they're asked, show the following is invertible and that this is the inverse. Oh, well, if they're telling you, and this is the inverse, they're giving you a huge hint on how to do it. Just take the conjectured inverse and see, does B times A times B equal the identity? So when they give you something like that, it makes it a lot easier. For the first part, we want to show that negative A times negative B is equal to A times B. And so what have we shown so far? All we've shown so far is if we multiply anything by 0, we get back itself. So any thoughts about how we want to prove minus A times minus B is A times B for all A, B in the ring? Any thoughts on how we might try to do this?
Try to do like -1R.
All right, so let's try it. So how would you? So we don't know -1 times A is negative A yet. We got that as a consequence of if we can prove this. We don't know this yet. So we just showed that if this is true, all we know is that if we multiply anything by 0, we get 0. So what I could do is I could start off with 0 times negative B is just what? Is 0. And how could I write 0? I could write it as B plus negative B, but I've already got a B. I could try it as A plus negative A. So I could write it as A plus negative A times negative B equals 0. So that would give us A times negative B plus negative A times negative B equals 0. So the additive inverse of negative A, negative B is just the additive inverse of A times negative B. We're trying to show negative A times negative B is just A times B. Did we make a mistake? Oh, sorry, there's not supposed to be a negative sign in front over here. It's just negative A times negative B is the additive inverse of A times negative B. So we were able to essentially pull out one of the minus signs, right? We pulled out the minus sign from A. Yes? So now we just want to do the same thing and pull out the minus sign of B. So now if I have A times 0, that would be 0, and that's A times B plus negative B. So AB plus A negative B equals 0, which implies A times negative B is negative AB. I'm just being really careful how I write things. So we substitute. We know negative a times negative b is the additive inverse of a times negative b, but we just showed that a times negative b is the additive inverse of ab. And what's the additive inverse of the additive inverse of ab? It's just ab. So one of the nice things for me about mixing up the classes is I don't have to do this twice. I did not prepare this ahead of time because I wanted to just go through the thought process. How would I try to attack a problem like this? Yeah, it's been nice. It's been 15 years plus since I've taught abstract algebra. So it's been a while since I've looked at calculations like this. And so it seems natural to prove part B, maybe part A could be useful. Doesn't have to be, but maybe there's a reason that they are given to us in that order. And in the first part, we prove that if you multiply anything by the additive identity 0, you just get 0. And so I was trying to look at what are different ways I can write 0. I can write a plus negative a. And then when we went through and did all the algebra at the end, we are then able to show that negative a times negative b equals a times b. The big hint is the in particular that's basically telling us that if you choose special values of a and b, then you get the next claim. So again, the goal for 355 is to help to teach you how to look at these problems, how to start coming up with these proof strategies. The number of questions we can ask you is almost unlimited. This is extremely hard. In a calculus class, there's really not that much I can ask you. It's pretty clear what I'm going to throw at you. So it's how do I attack problems like this? Okay, any questions about this? Okay, so the next is we're going to let R and R prime be rings, and a ring homomorphism from R to R prime is a function phi satisfying the following 3 properties. So the first is it sends the multiplicative identity to the multiplicative identity. It then respects addition. Phi of a sum is the sum of the phis. Now we have to be a little bit careful here. When I look at a plus b, where is the addition in a plus b relative to? This is addition in where? In R. And over here, where is this addition? In R prime. So it's not necessarily the same addition. We could put subscripts R and R prime on everything and just make it an absolute nightmare to read. So we just assume that when you see something like this, that you know I'm adding things with the correct addition law to that space. We similarly have issues with the multiplication. In A dot B, it's multiplication in R. In phi of A dot phi of B, it's multiplication in R prime. And so what does a ring homomorphism look a lot like? It looks like a group homomorphism. And in fact, phi of A plus B is phi of A plus phi of B. That's just a group homomorphism. Why can't I say that this is a group homomorphism under multiplication? It's not necessarily a group under multiplication, but it still has the property we would like. Phi of a sum is the sum of the phis, phi of a product is the product of the phis. And then we showed that in a group homomorphism, you send the identity element to the identity element. And so we are claiming that we will only consider a ring homomorphism if the multiplicative identity goes to the multiplicative identity. What do you think the additive identity should go to? So this is telling us that we must send the multiplicative identity to the multiplicative identity of R prime. Where do you think the additive identity 0R goes? Which identity? The additive, which additive identity? Of R prime. So does phi of the additive identity 0R equal the additive identity 0r prime. Well, we know it's got to be a phi of a sum is the sum of the phis. Can you give me a good choice of A and B to use? So we could do A and negative A.
A and the identity.
Which identity? So we have lots of choices. So one choice is if you look at phi of A plus negative A. Another choice was you said look at phi of A plus 0. And I'll give you another one, 0 plus 0. I think these are all three natural things to look at. So if we look at phi of A plus negative A, that's going to equal phi of A plus phi of minus A. What do we know about phi of minus A?
Minus.
Why?
Because A plus minus.
So we know this is phi of 0, but we don't know phi of 0 is we could write this as phi of A plus phi of negative 1r times A, and then use the fact that phi of a product is the product of phis. This is negative 1r times phi of A. But you can see that we need to know a little bit more here. So if we try A plus negative A, it's not a bad thing to try, but I'm running into some trouble. Now, if I do A plus 0, we know that that's just the same as phi of A, and then that's phi of A plus phi of 0. What must phi of 0 be? So phi of A is phi of A plus phi of 0. What must phi of 0 equal for this to be true? 0, because we can now subtract phi of A from both sides. And then we would get 0r prime is equal to phi of 0r. So the idea of looking at phi of A plus 0 was a really good thing to try. If we do phi of 0r plus 0r, well, that's the same thing as phi of 0. And that's going to be phi of 0r plus phi of 0r. And then just same as before, subtract phi of 0r from both sides. And then you would get 0r prime equals phi 0r. So both the second and the third choices both work.
Subtract phi of A from phi of A, then you get, why do you get prime there?
Well, because phi of A lives in R prime, right? So A lives in R, but phi of A lives in R prime. So when I add the additive inverse of phi of A, I have to get the 0 element in R prime. So really, the second and the third attempts are essentially the same. They're just, the third attempt is just the special case when A is the 0 element. The middle one is just take an arbitrary element A. So the first case is not working yet, but it's making us think that maybe phi of negative 1 should have a nice property. Now that we know phi of 0 is the 0 element, what does phi of negative 1 have to be? Negative R prime. So using phi of 0r equals 0r prime, the first idea gives 0r prime is phi of a plus phi of negative 1r phi of a. So phi of negative 1r has to be negative 1r prime, as phi of a and phi of negative 1r phi of a are additive inverses. Or we could use distributive law and just say we have the identity in R prime plus phi of negative 1r has to be 0 in R prime. So there's lots of ways we can now deduce that phi of negative 1r is negative 1r prime. So it's essentially saying that phi does exactly what you would hope it would do. We just force it to send the multiplicative identity to the multiplicative identity. It also sends the 0 identity to the 0 identity. So a lot of times in math, the question is, what is the minimal set of assumptions we need? We don't need to put in an assumption that phi sends the 0 element to the 0 element. We get that for free from everything else. The next thing is the kernel of phi is the set of elements that are sent to 0. So the kernel of phi is all a and r such that phi of a is 0r prime. Is the kernel ever empty? Is it possible that there's nothing in the kernel? Excellent. So we just showed that 0 is sent to 0, so we know the kernel is not empty. And then the question is, what else is sent to 0? And you might wonder, is the kernel a nice set? What kind of object might the kernel be? It might be more than just a set. What could it be? It could be a group. What else could it be? It could be a ring. So these are natural questions to ask. When I was a freshman year, there were like 5 standard questions you would ask when you met somebody. What's your name? Where you're from? What are you interested in studying? You had a little freedom for the other two, but they were just a bunch of natural questions. We have natural questions to ask. Are you a group? Are you a ring? So when I'm looking at the kernel, it's very natural to ask, is it a group? And if I'm asking, is it a group, I have to go under either addition or multiplication. Do you think it could be a group under multiplication? Not necessarily, because remember, we don't know that R is a group under multiplication because there could be issues with inverting the 0 element. So, I'm much more likely to believe that it's a group under addition, and maybe it's a ring. Okay. So we'll probably do more examples of stuff like that in Thursday's lecture. And then right now, I want to talk a little bit about some interesting examples of rings. So we're going to define the set, the ring Z mod MZ, to be the set of congruence classes. Okay, so this is basically our clock mathematics. And so the question is, do we have a natural addition? Do we have a natural subtraction? So, we say, x plus y is going to be x plus y mod m. And similarly, x times y is going to be xy mod m. But now we're defining it on the set of congruence classes. And so really, when you look at the congruence classes, for example, if m equals 12, we have 12z is going to be ... minus 24 minus 12 0 12 24 ... And then what's the next congruence class? could write this if you want as 0 plus 12z. And by cosets, what would the next one be? So you could view this as these are all the numbers whose remainder is 0 when we divide by 12. What would be the next one? I'm sorry? Okay, so but how would I represent it? What would be the coset? 1. 1 plus 12z. And then we got it off negative 23, negative 11, 1, 13, 25, dot, dot, dot. And go all the way down to 11 plus 12z. And then dot, dot, dot. So let's see, if I add 11 would be negative 13, negative 1, 11, 23, 35, dot, dot, dot. And if I took two things, a plus 12z, and I added to that b plus 12z, that would be a plus b mod 12 plus 12z. So for example, 8 plus 12z is one of my elements. I'll add, 7 plus 12z. What should that be? So 8 plus 12z, and I add 7 plus 12z. What should that equal? Three. Because what I'm doing is, it's 8 plus 7. I'm sorry?
I was gonna say, did you get that from doing like 15 minus 12?
Yeah, exactly. 15 mod 12. It's minus 12 because 12 only goes into it once, and the remainder is 3. So how many elements do I have in Z mod 12Z? I have 12 elements. 0 plus 12Z, 1 plus 12Z, 11 plus 12Z. And so I can view these as each of these is an infinite set with elements that are all equivalent. Or I could just view it as I just have these 12 objects and I'm using my clock arithmetic to add them. So, 8 plus 12Z plus 7 plus 12Z, that's 15 plus 12Z, but 15 plus 12Z is the same as 3 plus 12Z. It's just a different name for the same infinite set. And so sometimes it's nice to write it like this. Other times it's nice to write it more compactly with clock arithmetic and say, look, I've just got 12 elements that I'm working with. Is this going to be a group under addition? If I take two elements and add them, is it closed? Is there an identity? Is it associative? Yeah, what's the identity under addition? It's going to be 0 plus 12z. What's the identity under multiplication? It's 1 plus 12z. Is it a group under multiplication? No, there's nothing whose inverse, there's nothing that can be the inverse of 0. But what about if I looked at the non-zero elements? Do the non-zero elements form a group under multiplication? So do the non-zero elements form a group under multiplication? Why not? Good. So if you look at, oops. So there's no inverse for 2 plus 12z. If you look at 2 plus 12z, everything in 2 plus 12z is going to be a multiple of 2. If there's going to be a multiplicative inverse, when I multiply it by that, I've got to get a remainder of 1 mod 12. And there's nothing I can multiply an even number by and get an odd number. What other elements would not have a multiplicative inverse? So 2 fails to have a multiplicative inverse. What else fails? Any of the evens, so 2 fails, 4, 6, 8, 10. Okay, can somebody give me someone else give me an example other than an even that fails? So can you give me a number? So we saw multiples of 2 don't work. Okay, but multiples of 12, that's really the same as the 0 element, right? So 0 doesn't work. Multiples of 5. Why multiples of 5? Well, let's think. Can you think of something that if I multiply it by 5, I'm going to get 1? Yeah, if I actually multiply it by itself, it turns out that that is 1. So some non-zero elements do have multiplicative inverses. So 5 does have an inverse. Can you give me a number that doesn't have an inverse? So the problem with 2 is 2 always has a common factor with 12. So they're always going to be multiples of 2. There's nothing I can multiply 2 by and have a remainder of 1 mod 12 because 2 and 12 share a factor. Good. So give me another factor of 12. 3. Yep. 9 would also have trouble because 9 shares a factor with 12. So if we share a factor with 12, we know there's trouble. If we don't share a factor with 12, there may or may not be trouble. It turns out in this case, we can find an inverse for 5. Similarly, we could find an inverse for 7. Amazingly, it's going to be itself. If we try to find an inverse for 11, turns out it's also itself. The inverse for 1 is not so bad. That's also itself. So every element is its own inverse. So this is an interesting example of a ring. And it is a ring where we have some elements that are invertible and some elements that are not invertible under multiplication. And you can't just say, throw away the 0 elements and what's left over is going to be a group under multiplication. Nope, we have some non-zero elements that still cause trouble. Okay, for another example of a ring, here is what's called the Gaussian integers. So what does I equal? Anybody remember? Is the square root of -1. So I squared equals 1. So this is a really interesting set of numbers. And you should have hopefully, seen these before, in the complex numbers, z equals x plus iy. And so it turns out that this is going to be a ring. And we need to figure out how do we want to define addition, how do we want to define multiplication. So if I give you a plus bi and c plus di, how should we define addition? A plus c plus b plus di. And then multiplication, a plus bi times c plus di. Well, if we just use our standard ways of multiplying things, well, it would be ac plus bci plus adi plus bdi squared. So what does I squared equal? -1. So this is AC minus BD plus BC plus ADI. And so this gives us a good way to define addition and multiplication. And now you just have to go through and show that this is a ring. 0 element B under addition. How would you write 0 in this form? So it's all numbers of the form a plus bi, where a and b range over the integers. So how would you write 0? 0 plus 0i. This is being extremely pedantic, right? And what would the multiplicative identity be? Let's just get. So what do you think the multiplicative identity should be? So there's a typo here. It's I squared is not 1. I squared equals, that's a bad typo, equals -1. What should the additive identity, I'm sorry, the multiplicative identity be? You're just looking at numbers. When you think of identity for multiplication, what do you think of? It should just be 1 plus 0i. So I need to write my stuff in this form. Now I need to show closure that if I take two numbers of this form and add them, is it still going to be of the form integer plus integer times I? Yes. If I multiply them, will it still be of the form integer plus integer times I? Yes. Again, I'm not saying that I have multiplicative inverses. And so now you just go through, and now we have, these are the identity elements. And you can now just go through and verify that all the properties hold. Okay. So again, it's just a question of trying to identify what should the elements be. I don't want to just write 0. It's technically 0 plus 0i. But by an abusive notation, we would just write 0 for that. And by an abusive notation, we would just write 1 for the other one. We're not going to carry this. This is similar to when we did the binomial coefficients in Pascal's triangle. When we proved Pascal's relation, we really had a 1 choose 0 and a 1 choose 1 floating around. But what's 1 choose 1? How many ways are there to choose 1? 1. What's 1 choose 0? Also 1. So there's no need to keep writing it down. So sometimes when you don't have this extremely pedantic, long, painful notation, it actually causes confusion because you might forget where things live. And so it's not so bad to just write out the 0 element is 0 plus 0i. The additive, the identity under multiplication is 1 plus 0 times I. Okay, another example is polynomial rings. So given any commutative ring R, so what does it mean for R to be commutative? Yeah, so when we multiply, so commutative here, it means AB equals BA. Why don't I have to say A plus B equals B plus A? Yeah, we define a ring to be commutative under addition. So when we say that the ring is commutative, that means it's also commutative under multiplication. So what they're saying here is a commutative ring, R, gives rise to a polynomial ring. And so Rx is going to be all polynomials of all possible degrees with coefficients in R. So why not consider R sub 2024 of X is going to be all polynomials, A0 plus dot 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 plus A 2024 X to the 2024, where each AK is an R. Is this a ring where I look at all polynomials of degree 2024? What do you think? So this is a ring? Is it going to be a abelian group under addition? If I take two polynomials and add them, is it going to be closed? Is it going to be associative? Will there be inverses? Will there be an identity? What should the identity element be? Identity under addition. So it's just going to be 0 plus, 0x plus da 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 plus 0x to the 2024. What's the identity under multiplication? And then 1 plus all the zeros. So is everybody comfortable that this is a ring? All the properties hold? So we're comfortable that everything is good under addition. You seemed a little concerned, or?
I feel like I'm trying to think of.
Well, what do we have to check for multiplication? We just showed that there's an identity. Do we have to worry about inverses? If we're trying to show that it's a ring, do we have to worry about multiplicative inverses? Doesn't have to have multiplicative inverses. Not necessary, so we don't have to worry about that. Associativity, that should inherit associativity from standard things. What's the last thing we need to check? I'm not saying that the polynomial ring is commutative. There's one other property we need to check. It is the most forgotten of property. Well, we technically do have to check distributive, but there's something else under multiplication. We checked identity, we checked associativity, we don't close. So if I take two polynomials of degree at most 2024 and I multiply them, do I get a polynomial of degree at most 2024? No. I really, really, really want to drive this point home. Okay, unfortunately, it's not closed. And so, for example, x to the 2024 times x is x to the 2025, and it's not in 2024. And this explains why when we were looking at it, we said of all possible degrees. Now, I'm never looking at an infinite polynomial. I'm never taking a polynomial with infinitely many terms. I'm just saying it's all polynomials with a finite degree. If I have two polynomials with a finite degree and I multiply them, do I get a polynomial with finite degree? So if I have two polynomials with finite degree and I multiply them, that will still have finite degree. So it will be closed. But if I looked at all polynomials of degree, at most 2024, unfortunately, that would not necessarily be closed. So again, it's very easy to have a property miss. What you have to do is you have to be very methodical. You have to go through all possibilities. Okay. Another example is the evaluation map. So I can take this polynomial ring, and I have a map from the polynomial ring to the ring R, and it's defined by take your function and just evaluate your function at the point C, where C is some element in R. So here, C is in R. Okay. So when we look at this, the claim is that this is a ring homomorphism. So we now have to go through and prove all this. So in Thursday's lecture, I will probably prove this in section 2 and just go through and show that this really is a ring homomorphism. And then it says the kernel is a really interesting set. It's all polynomials that have a factor of x minus c. Well, if it's a ring homomorphism, what does 0 have to go to? So for ring homomorphism, what does 0 have to go to? It has to go to 0. So when I evaluate the polynomial at C, if I want it to go to 0, this is basically saying you need to be a multiple of x minus 1. So the ring homomorphism sends 0 to 0, not the same 0. So if f of C equals 0, saying f of C equals g of x, okay. It's saying f of x is g of x times x minus c. The only way a polynomial is 0 is if it is a multiple of x minus c. And then the question is, does R need any special properties? For this to be true. So for example, maybe I take R to be the ring Z mod 12Z and look at R of X. And maybe I could take C equals 4. I could look at maybe f of x is 3x. Then if I take the evaluation map where my value of C is 4, this is just going to be f of 4, which is going to be 12, which is going to be the 0 element. So is this going to be the same as x minus 4 divides f of x? Oops. Does x minus 4 divide f of x? Well, I could write this as, 3x is 3x minus 4 plus 4. This is 3x minus 4 plus 12. But what's that the same as? If we're looking in the ring Z mod 12Z, if I add 12, that's the same as adding 0. So that is the same as 3x minus 4. So maybe this is a reasonable claim. When I look at 3x, that does not look like it's a multiple of x minus 4. But we just showed that, remember, you can often write something multiple ways. All right, so this is a good place to stop. And then again, what we will do is on Thursday, this class will be doing problems and the other class will be doing theory.